Okay, let's take a look at the last problem. So the goal is to design a sequence detector. So the first one is to draw the sequence detector timing that state diagram similar to this one, and the instruction you can find on the website. I'm going to show you how to do these similar problems in a bit. Okay, so you'll know how to do it. And B is sequence detector to detect 1010. Okay, you want to draw the state diagram, truth table, logic expressions, and behavioral Verilog model. Okay, you shouldn't use the state. What's the name of that? Structural. So it's asking you to do the behavioral instead of the structural, and implement it using the on the basis 3 board. Serial input must be taken by switch. So what's going to happen is you are going to input the code here, just any random binary code. Okay, until you see 1010 in a row, it triggers it. You know what I mean? So the customer is allowed to do no matter how many binary inputs they want to do. It just keep inputting any kind of random code, but whenever you see a 1010 in a row, it triggers it. Okay, so do need a state machine. So you need a sequence detector to do the job. So here's a sequence detector to do the transition in between all the states. If you're able to design a sequence detector based on this similar timing, the state diagram, and you just need to provide the input and output, it should be able to do the job, because the block will do whatever it's designed to do, right? It's going to do the job, do the sequence detector. You don't have to worry about that. So it's going to be a very similar coding diagram compared to the example on the website. Okay, so definitely you need the debounce. And this is a D flip-flop to register the code, whatever the data is available on the switch. Okay, and need the clock for the VGA and for the debounce as well. Okay, so 100 megahertz clock available on the board, and the VGA monitor will show a green color, just solid green color whenever the 1010 code is being detected. Otherwise, it's always showing red. So what's going to happen is whenever you see that 1010 in the row, it triggers a green solid color on the VGA. And if you keep adding more code to it, it should turn it back to red until you see 1010 again. You know what I mean? So it's very doable because the state diagram is going to do the job. So don't worry about that too much. These are just the interface. Whenever the sequence is being detected, it's going to send a signal to the VGA. You just need to add one signal line as an input for the VGA controller. Definitely you are allowed to copy and paste the previous code we have created in the past tutorials. VGA cable connect to the monitor. Okay, seems reasonable to make it due on Thursday, 5:30 p.m. What do you think? Global? Okay. So the sequence detector, I don't think we talk about the details of it during the tutorial, but you can see this is a sequence detector, and if you are trying to design a different detector for different sequence, for example, it's a random sequence, for example, 1001, okay, 4-bit. Because we have 4 bits, so we need 4 states. And the name, because it's 4 states, you just need 2 bits, 2 memory bits, to make 4 possibilities. You just code it up. These are just named for the states, 0001, 1011, right? You can imagine the customer is keep inputting the binary code into the machine. Okay, this sequence could be in between any binary code. You know, you may have like this in the front of it or whatever, and the trailing zeros, trailing ones, whatever. Okay, it's all the different possibilities. But whenever this 1001 happens in a row, it triggers it. right? That's a rule for this state machine. Okay. So for example, if we detect a 1, if you detect the first one, okay, you see a 1 there, and you want to transition you want to transfer to the second state because you see a 1 here, and then you should wait for a 0 instead of a 1 as a state. Okay, if you see a 1, it should be a different state because now you're waiting for a 1 instead of a 0. And you're waiting for a 0 instead of a 1 anymore. Because the sequence starts with a 1, right? So whenever 1 happens, you move to the next state. And for I think that's a milli state machine. So it's input and output. X is the input, Y is the output. So for your sequential circuit, you got X as the input and all the D flip-flops to hold the states. You don't have to worry about that. And there will be a final output called 1. Okay, so you have all the inputs and outputs being labeled on the arc. So for example, the input is 1, so you move to the next state, and output is 0 because it's not triggering the signal yet because they're not finishing the sequence yet. Okay, so whenever you see a 1 as the input, okay, that's the X on the left, and then you output a 0 because it's not finishing the sequence yet, but you do want to transfer to the second state because now you are waiting for a 0 instead of a 1 anymore. Okay, don't worry about the name of it. You can name it whatever you want. It's just the 0, 0 is the name of the state. You have 4 states, so I use 2 binary bits to represent it. So that's a state 0, state 1. So from here, what if you keep having zeros? If you keep the input is always zeros, what's going to happen? You always stay at the state 0, right? Okay. If you see a 1, you move to the next. So now I already have a 1. So what if I keep having 1s at this state? For example, I keep having 1s. What's going to happen? Yeah, output 0 and stay here, okay? Right? Because you just wait for a 1 that will be followed by a 0, then you trigger it, you move to the next. But otherwise, you just stay here. Okay, we just said if you have a 0, you move to the next. So you have an input at 0, and output is 0 as well because it's not finishing the sequence yet. So we can see the input right now we have 1 and 0. Okay, so these are the 2 inputs, 1 and 0. Since we want to finish 1, 0, 0, 1, now we are here. Okay. So we move to the next state. You are waiting for another 0. But what if when you are waiting for a 0, you are waiting for a 0. What if you have a 1? It's going to kick it back, right? So you're waiting for this 0. But however, if you got a 1, what's going to happen? You want to return to where? What? No. Because you have to return back to the first, to here, right? Because you got a 1, you're waiting for this 0, but it's not 0, it's a 1. So it's here. So return here, right? Because you got a 1. So return here. Is that correct?
Which one are you looking at? The one on the midterm? He's doing a different one.
Oh, okay. Sorry.
Yeah. I was like that. It was throwing me off as well.
Okay. That makes sense.
So I'm detecting 1001.
Yeah.
Yeah. So 1, 0, and then got a 1. So I want to return to this state, right? So what if I have a 0? Move to the next. So now I'm here. So I need a 1 to finish it. Oh, done. So that's why I want to send the signal 0, the 1, to finish the sequence detection. So now the only thing left is over here. If I have 1, let me label it, 1, 0, 0, okay? And then I got a 1, so I'm done. So return back here. So what if I, do you want to return back here or here if you got a 1? If I got a 1,
You go back to 0.
yeah, I think so too, because we want to finish the whole sequence. We don't want to reuse this one as the starting of another 1 0 1 1 0 1 0, right? We need to finish. Oh, sorry, 1 0 0 1.
Would you?
We don't want to reuse it. We need another one to start 1 0 0 1 again. This is done. This is one sequence. We need 4 bits to finish the sequence. So 1 should be. If you got a 1 as the last one, you should return here, okay? If you got a 0, what's going to happen? If you got a 0, you are getting actually 1 0 0 0, right? You only allowed to have 2 zeros in the middle. So if you got a 0,
So you're saying that you don't.
if you got a 0, go up to the first, right?
Yeah.
Here,
Yes.
yeah. So what if I want to detect? Yeah, I think that's legit as well.
Because you're
Let's do
detecting.
that. That's more.
You're detecting a serial.
Yeah, that's right.
So it'll like, it just looks at the last 4 digits,
Okay.
no matter what they were.
I agree with you.
Okay. Thank you.
That correct?
Yeah.
Okay. Similarly, you work on the problem that we have here. So this is the one from the website, and you got another one to create by yourself, 1010. Okay. Similar idea. So another question is, if you have the state diagram drawn already, what's the next? If you look at here, okay, what's the next step? Truth table. Okay, how do we convert the state diagram to the truth table? We just look at it. See, this is 0 0 as a first state, right? So I have 0 0 here, and the next state is 0. If the next state is 0 0, you need the x to be 0 and y to be 0. So just fill it up in the table. Okay, and then you can look at each column to find out the logic expressions. It's super simple. You have 1 1 1 3 ones over here, and just use the midterms in logic, learn logic, and find out the logic expressions like this. So you can draw the. Oh no, you don't have to draw the circuit diagram because they are not designing a sequential circuit on the breadboard. If you are trying to design the circuit on the breadboard, you do need to draw the circuit diagram, right, with the D flip-flops. You can find a D flip-flop chip in the lab, and then you have to convert this logic expression into the circuit sequential circuits, and then you can wire it up on the breadboard. But now we are doing Verilog in basic 3 board, so eventually they'll be synthesized by the IPGA, so you just code it up. Okay, so 3 steps. First step, find out the state diagram. Second step is the truth table. The third step is logic expression, and then directly code it up in Verilog and synthesize it, right? Make sense? Okay, that's everything I want to talk about.